Okay, can you see it, the slides?
Yes.
Okay, perfect. So, as I said before, thank you very much for the introduction, Massimiliano. And I want to thank you, to thank the Polyme Data Scientist Association for the invitation for this talk. The title of the presentation is Knowledge Graphs from Semantic Technologies to Relational Artificial Intelligence. This is the agenda of the talk. First of all, I will introduce the main idea behind the concept of knowledge graphs, and then I will try to explain the meaning of the claim things, not strings. Then we will see how we can use different primitives such as graphs, symbols and vectors in order to represent knowledge graphs. Finally, I will show you some application scenarios for the knowledge graph technologies. Actually, there is a ton of context in which the adoption of knowledge graphs is very useful, but I focused on a subset of them that I have addressed during my PhD program. Before going into the presentation, I would like to spend a couple of words on my background. This picture belongs to my recent research experience. In fact, this is a picture of the community of the Nexa Center for Internet and Society. Nexa is a community that includes academics and experts with different backgrounds, from engineering to economics or social scientists, etc. And its main goal is to studying the internet with an interdisciplinary approach. In the Nexa Center in September 2020, I received my PhD in computer engineering. And this is my present. I currently work at Synapta. Synapta, as mentioned by Massimiliano, is a 5-year-old startup that is focused on the data integration and extraction for business intelligence. Moreover, Synapta is included in a rich ecosystem of research centers, incubators, venture capitalists, and companies, such as, for instance, Sally, that is a natural language processing company. And the main project of Synapta is called Contratti Pubblici, and contrattipubblici.org is a search engine that indexes and allow you to explore all the Italian public contracts. It currently gathers more than 50 million of contracts. And in 2019, this is really interesting information, Synapta customers using these tools have won contracts with the public administration worth 19 billion of euros. Okay, let's start our journey with this slide that presents an article released from Google in 2012. This article was entitled Introducing the Knowledge Graph, Things, Not Strings. This article actually explains that for more than decades, search on the internet has essentially been about matching keywords to queries. However, the keywords and the words that you use during our life have specific meaning. So, for instance, if we take the word apple, the keyword could be the fruit or the company in Cupertino. To consider the impact of such things and not just strings for search engines, consider the following example. If we type on Google, who was the director of Lolita in 1962, the answer is Stanley Kubrick. But if we type who was the director of Lolita in 1997, well, the answer is totally different because the answer in this case is Adrian Lyne. So the capability to distinguish between two different entities according to the natural language question that you can type on Google is enabled by a knowledge graph. And a knowledge graph is a collection of nodes that can be linked through a collection of relations. This is an example of knowledge graph in the cultural domain, in which you have, for instance, different types of entities, including directors, screenwriters, movies, and books. And you have different edges or relations between these entities. As you can see in this knowledge graph, Lolita can be at the same time a book here, or a movie directed by Stanley Kubrick, Guardian Line. So in this case, you can have different type of entities that can be recognized using the same, let me say, keywords. So giving a more formal definitions, knowledge graphs have become a core abstraction for incorporating human knowledge into intelligent systems. This knowledge, as we saw, is encoded in a graph-based structure in which nodes represent entities of the real worlds, while edges define the relation between these entities. Large-scale knowledge graphs are gaining attention from both the industry and the academia in different domains, for instance, from finance to life sciences. This is an example of a dashboard provided by the Alibaba Group, which is not only, as you can see, involved in e-commerce stuff. And this dashboard is particularly useful for risk detection and recognition that is fundamental for investing in the financial market. Let's see another example that is related in this specific case to life sciences. Here you can see a Medium article related to AstraZeneca, which is currently quite famous, that describes how knowledge graph technologies are applied to predict novel disease targets. Until now, we have seen corporate knowledge graphs, which are not directly available and explorable by the user using queries. In this case, actually, this is a cloud, or let me say a network of interlinked knowledge graphs that are freely available on the web. In this case, each node represents a data set, and the connection are the direct link between these data sets, and the color represents a specific domain. As you can see also in this example of open knowledge graphs, the red cloud or maybe pink cloud includes all the open repositories in the domain of life sciences. Well, after this brief overview of knowledge graphs, let's provide some details on how we can represent knowledge graphs. This aspect is particularly interesting because according to the specific representation, different tasks can be addressed and different research communities are involved in the process. Let's start with the graph representation. And I believe that all we know that a simple graph structure includes a set of nodes, which are connected by a set of edges. In case of a knowledge graph, these edges are directed. You can have multiple edges between two nodes, and these edges are characterized by a specific label. Actually, in a knowledge graph, a different type of attributes can be assigned to both nodes and edges. For instance, a person has different attributes, such as his name or her name, or his age and her age. But from a graph perspective, this relational structure is the most relevant one. The interesting thing is that this graph structure can be represented in different ways. We can represent this graph using a symbolic representation or using a vector representation. Maybe in your direct experience as a data science students, you are more familiar with vectors and embeddings, but in this presentation, I will give you some details on both symbolic and vector representations. In the case of symbolic representations, the nodes define entities of the real world, and the edges define the relationships between these entities. Traditionally, the starting node is called subject, the end node is called object, and the relation between them is called predicate. So we can see edges within this graph as a sort of, let me say, collection of statements or facts. In the case of vector representations, the entities and the relations are represented in a high-dimensional vector space. Now let's provide details on the symbolic representation. From a symbolic perspective, a knowledge graph can be seen as a semantic technology. As we said before, different research communities can treat knowledge graphs as semantic technology. For instance, there is the logic research community that focuses on the inference of new edges in the knowledge graph using deductive reasoning. For instance, the statement a director is a successful director could be true if and only if this director received an Academy Award. It could be true or not, it doesn't matter. It is a specific rules that can be introduced and then derived from the knowledge graph. We can see knowledge graphs also as an implementation of graph databases. But in the next slides, I will provide some more details on symbolic representation and how this symbolic representation can be adopted for the task of semantic data integration. I will focus on this specific task because I covered it during my PhD, and later I will show you some interesting, maybe interesting applications. Okay, let's back to our running example. As we can see, this knowledge graph can be represented using triples, facts, or statements. And this collection of facts can be seen as a graph because the destination node or the object of these statements can be also a starting node, as in this case. So we have a graph representation through statements and facts. Behind these facts or statements, there is, let me say, a sort of semantic skeleton that is known as ontology. The ontology defines the semantics of the entities and the relationships in the knowledge graph. The ontology can also be represented as a graph in which the nodes define the classes of our data, for instance, people, directors, writers. In this specific graph, the Greek-colored arrows define a subclass relationship. For instance, a cultural object, in this case, is a book, while the black-colored arrows define the object properties that describe the semantic relations between the classes. For instance, in this case, a writer is an author, it can be an author of a book. So the ontology represents the semantic skeleton that describe the meaning of the knowledge graph that we can see in the right side of this slide. Ontologies currently can be defined using specific languages such as RDS schema or web ontology language. And this language can allow you to represent a graph using symbolic statements. All these statements maybe are intuitive, but the last one maybe could be more interesting one because it expresses an important detail. In this case, okay, a person can be at the same time a writer or a director, but according to this statement, a movie cannot be a book. So this property called is disjoint from means that the collection of books and the collection of movies are true disjoint sets. Well, from a semantic perspective, what is the difference between these statements and the statements that we have seen here in the previous slide? These statements are true by definitions. In fact, in a formal way, they are also called axioms. And they are true in any data set that we want to model according to the specific ontology. So if you want to describe the cultural domain or in Europe or the cultural domain in Asia, the statements that you can see in these slides are always true. So they represent a high-level perspective on our data. Another interesting type of reasoning that we can perform using knowledge graphs is related also to the instances of the data and not only to the ontology. For instance, consider these two relations in red. From the point of view of reasoning at instance level, these two relations are both correct. Well, it depends, because if we state in our ontology that a book is based on a movie, if and only if the author of the book is at the same time the screenwriter of the movie, well, according to this rule, the relation in red is the valid one, because Nabokov is at the same time the author of the Lolita book, but at the same time is also the director of the Lolita movie that has been directed by Stanley Kubrick in 1962. So all these examples show you that knowledge graphs is a semantic technology in which a collection of rules can be introduced at different levels. The useful thing to understand in this specific case is that the inference of all these rules is predictable, and more importantly, is also interpretable. And it's a really important feature because, as we probably know, artificial intelligence in the field of deep learning is not so interpretable in many cases. So here I leave you a Medium article that I write in which I tried to elaborate the notions that I have just explained to you. So for further details, this is a reference reading. Now let's see how the representation can be used for a specific purpose. The main idea of data integration from a semantic perspective is to map the local schema of different data sets to global schema, in our case, the ontology. In order to clarify this aspect and this definition, I will give you an example. So consider this set of multiple sources that employ different storage technologies and schemas. So each of these, let me say, database includes its own language in order to storage and publish the data. On top of these different sources, we can put a semantic layer, or in other words, an ontology, which is able to describe the same semantics of the data that are included in these different databases. Because in many cases, different databases can, let me say, have overlapped information. Because for instance, if all these databases include information on Turin, one database could be much more focused on the, let me say, on the population, while another source can be focused on geographical information. And but they talk about the same things, as we mentioned at the beginning of this presentation. So the idea is to map the local schema that belongs to these to all these different multiple sources to the global schema of the ontology. When we are able to perform this mapping process, at the end we can able to generate a knowledge graph that is a graph that has a graph representations, and for these reasons it is more flexible. It can be used to describe the semantics from different schemas of the original sources. Also in this case, I will leave you another article that you can explore in order to receive much more details on this specific topic. Now let's talk about the vector representation. In the previous slide, we see details on the symbolic representations. We have seen an application domain in the context of a semantic data integration. Now we will see knowledge graphs from a different perspective. Knowledge graphs actually are involved also in the research activities of other communities. For instance, for computer vision, knowledge graphs are exploited to encode the relations and the activities that are performed by the objects and the entities recognized in an image. In case of natural language processing, many tasks are focused on building knowledge graph statements from textual information. And this is particularly useful task because we can treat the text as a graph. And in this case, for instance, we can perform queries or other type of analysis. Another example in the context of natural language processing is named entity recognition. So the task in this specific case is to recognize a specific entity in the text. So if you remember the Apple example, if we encounter the Apple word in a document, we should be able to recognize if this apple is the name of the fruit or the Cupertino company. In this presentation, I will focus on another type of research activity that is called graph representation learning. So we will see how to use the relational structure of a knowledge graph to predict, for instance, a new link to different nodes. So as we said before, we can represent nodes and edges as vectors in the vector space. This is not a high-dimensional vector space. It's just a two-dimensional vector space. And as you can see in a pure vector representation, we do not have the notion of meaning or semantics of the nodes in the graph. We just see numbers. And as you probably know, these vectors can be the result of a training process in which a representation learning algorithm has been able to recognize hidden patterns in the data and assign a vector representation, for instance, to the nodes. Maybe you have heard that the name of these resulting vectors is embeddings. You have heard them in case of natural language technologies. In general, as human beings, we are not able to understand their meaning. However, they describe a sort of, let me say, distributed semantics. The main idea behind the concept of distributed semantics is that, for instance, similar nodes can have and are characterized by a similar vector representation. Considering these graph nodes and edges, we can perform typical machine learning tasks, including, for instance, the link prediction. Here on the right side of this slide, you can see that these facts that are represented by these vectors can be considered true or false, and they can be used as training for a machine learning algorithm. But in the specific case of knowledge graphs, we have also an attached, let me say, semantics to these vectors. So in this specific case, we know the semantics of the nodes, and we can see that actually these embeddings represent, closer embeddings represent the same type of nodes as in this case. And these semantics can be applied also to the facts that are represented by the embedding vectors. This is particularly interesting because if we try to predict a new edges like this one, when we automatically know that our algorithm predicts something that is wrong. Because as we know from the semantic perspective of knowledge graphs, that a director cannot be a director of another director. And this is interpretable, let me say, and understandable because we know the semantics behind the vectors represented the knowledge graphs. For this particular discussions, I suggest this reading on you. So now now we will go in details of the graph representation learning techniques. In particular, we will see how to learn representation in the vector space from graph structured data using neural architectures. Graph neural networks have become the standard toolkit for analyzing and learning from data on graphs. Okay. Sorry, I just have some problems with the button. Just give me a second. Okay. In the following slides, I will talk about a specific techniques related to graph representation learning, in particular, graph neural networks. Graph neural networks have become the standard toolkit for analyzing and learning from data on graphs. These neural architectures are able to compute the node representation, aggregating the neighbor features. In general, different graph neural network architectures performs different types of aggregations. For instance, we can compute the average of the neighbor features, or we can concatenate the vector representation of the nodes, or we can also learn a differentiable parameter that is able to allow us to recognize the contribution of different neighbors to the central node. These aggregate features then can be employed for different tasks, including, for instance, edge predictions that can be useful for our task, for our example task. Now let's see in details what happens under the hood of a graph neural network. Consider a featureless representation. So in this case, we use one-hot encoding vectors. The idea behind one-hot encoding vectors is similar to the word vocabulary, in which the length of a vector is equal to the number of words in my vocabulary. And in this specific case of the graph, the length of these one-hot vectors is equal to the number of nodes. So in these one-hot encoded representations, all the elements of this vector are 0, except a single one element in a different position for each node. This featureless representation does not convey much information because we are able to distinguish only one node from another, because we have one element in a different positions, but we are not able to encode any type of feature related to these nodes. So for this reason, the first step is to project or embed the one-hot vector in another vector space. The length of the vectors in this space are now independent from the dimension of the graph. In general, their length is less than the original length of the one-hot encoded representations. And the numbers included in this vector space are traditionally randomly initialized. The training process will update these numbers in this new vector space in order to learn the so-called embeddings. So the embedding representation of our nodes. Obviously, the projection is performed in parallel for all the nodes in the graph. And at the first layer of the graph neural network, we aggregate the feature of the neighbors to the central node. Now, node 1 encodes in some way the local graph structure of its neighbors. In general, as we said before, different graph neural network approaches use different computations for performing the aggregation. And we have to clarify that also this aggregation process is performed in parallel for all the nodes included in the graph, according to the edges. You can think the edges as a sort of bridge between the nodes, and the aggregations as a sort of message that, let me say, cross the bridge to reach another node. In order for using, for example, the metaphor of Facebook, the main idea is that in order to predict an interesting page, an interesting page or an interesting community for me, the algorithm considers my features, but it also considers the features of all my neighbors. That's the main idea. And as obvious, we can add and introduce in the neural architecture multiple layers. And stacking LGNN layers allows the network to build a node representation from the hello neighborhood of each node. So the main idea is that the new representation of this orange node is the result of aggregation of its local graph structure. These are some technical details, but I believe that they are really useful in order to understand what happened under the hood of a neural architecture that is able to follow the topology of a graph. So actually, this works in case of graphs in which a single edge connects two different edges. But as we can see in knowledge graphs, we should compute a different type of aggregation for each relation type. So in this case, we did only the blue edge type, while in this specific case, we have 3 different edge types that connect to these 2 nodes. So we can perform the aggregation process considering also these multiple relations that can connect to different nodes. And this is particularly important, in particular for a scalability discussion, because if in this case, the number of parameters of our network depends only on the number of neighbors, in this case, the number of parameters depends on the number of edges. So not only on the number of neighbors that are connected to this node. So in this case, in many neural architectures that are able to encode the knowledge graph structures, we will use a lot of, let me say, techniques in order to reduce the number of parameters. Once we have computed this aggregation process, we can perform now a link prediction task. And we can use the representation of the subject and the representation of the object that are resulting from the previous GNN layers. So in this case, the representation, this vector, encodes in some way the local structure related to the subject node. These vectors will become, as we said, the parameters that that will be learned during the training process of during the training process. And the traditional, let me say, approach in order to train a neural architecture is the negative sampling approach. The main idea is that in order to train my network, I use the existing facts or statements as positive examples, and I produce in a random way the negative examples, creating facts that that do not exist in the original knowledge graph. So creating these negative samples, I can treat my learning problem, my link prediction task, as a classification problem. Yeah, this is another slide that shows you that actually behind these vectors there is a semantic representations of nodes and the edges. These are the other readings. This is a complex, actually, complex argument. So I share with you, I share on Medium different articles. In particular, I suggest you, if you have a little bit idea of neural network, I suggest you to read this second article entitled "Graph Neural Networks for Multi-Relational Data." This is particularly useful because it can show you, shows you how the number of parameters explode when we try to encode the structure of multi-relational graphs. So in the third part of this presentation, in the last part, actually, we will see how we can create applications exploiting both this representation of knowledge graphs. So building applications try to hybrid these two different perspectives of knowledge graphs. And we will see how this combination of the two representation can be used for the automatic semantic data integrations, so to automatize the process that I've shown you in the previous slide. We can see how these applications can be used for link prediction in order to address recommendation tasks. And we will see how this hybrid technology can be used for creating unexplainable artificial intelligence. Actually, the first two applications represent scenarios in which I developed something, I developed some tools, while the last one is the result of some reflections on hybrid systems that involve both the perspectives. So let's start with the automatic semantic data integrations. In order to clarify the process of automatic semantic data integration, I provide you just a brief recap on the concept of semantic model. Here I will show you some formal definition, and then I will clarify this definition using examples. Semantic models actually are graph structures that are able to define the precise meaning of the data. So these graph structures is able to bind the local schema of a data source, for instance, the attributes of an XML files, and the global schema of a knowledge graph. And this is represented by the classes and the properties of an ontology. Semantic models actually can be translated into mapping languages. So the transformation between the local schema and the global schema can be formalized using languages and not directly encoded in our source code. And these mapping languages can be used for generating knowledge graphs. This is a really particular detail that is related, is retrieved from the semantic web community. So in order to clarify the concept of a semantic model, I will show you an example in the public procurement domain, so in the public contracts domain. Traditionally, public procurement is the process by which public authorities purchase goods or services. In general, the authority announces a call for tender, and companies participate in this call with a specific tender. The authority shall award one of these tenders. I have analyzed the case study of Italian public procurement data that are currently ingested by Synapta in order to create its semantic search service. This is an example of XML that is currently published by the administration. And consider, please, these XML attributes, which include the identification code of the contract, the identification code and the business name of the contracting authority, so of the public administration, and the ID and the business name of the company, of a company which participates in the call for tender. So after the selection of these data source attributes, consider the following ontology graph that covered the semantics of the data in the public procurement domain. As we said before, the nodes define the classes of this ontology graph, while the edges define different types of properties. The semantic model is a graph in which the leaf nodes are represented by the attributes of our data source, while the other nodes and edges are built using the components or a subset of the components in the original ontology. As you can see in this slide, the semantic model is able to describe in an explicit way the implicit meaning that is, let me say, hidden in the source attributes. Here in orange, I have highlighted the subset of the components of the ontology that are adopted for the semantic model generations. So in our task, we want to automatize this process. We want to automatize the generation of the semantic model, starting from the attributes of a data source and a reference ontology as a description of my domain. Building semantic models then require to automatize two main steps. The semantic type detection, whose goal is to identify the class and the data property to label a source attributes. For instance, in this case, the source attribute CIG can be labeled using the class contract and the data property identifier, as you said in this graph representation. Then the second main task is the semantic relationship inference, whose goal is to recognize the path or the relation that connects two classes. In our example, we can have path of length 1 that connect, for instance, in a direct way, a contract and a business entity. And or you can have a path of length 2, for instance, because a contract can be connected to a business entity by a tender class. If you see the previous example, here you have a contract, here you have two business entities, and here you can see a direct relation. So the path in this case is as length 1, while in these other cases, the connection is a path of length 2. Just to clarify what is the semantic relation. And actually in my PhD, I focus on the second task because most of the work on the automatic mapping of data sources to ontologies focus on the detection of semantic types. However, a precise mapping that fully recovers the intended meaning of the data needs to describe the semantic relations between the semantic types. In order to address these tasks, so the automatic inference of semantic relations, I developed this architecture. Here you can see the main blocks of these architectures. I will not go in details, but if we have time, we can back later on this slide. The main idea is this architecture is that we can start from multiple semantic models. So in this case, you do not have a unique semantic model, but you have a collection of all plausible relations that can be in the semantic model. For instance, this contract can be connected by business entity, to this business entity, by this edge or this path. So we needed to guess which is the correct one. Well, the idea that I developed during my PhD is to assign some costs to the edges of these paths. Because if we are able to assign specific cost to these edges, we can perform some algorithms in order to identify, for instance, what is the shortest path that connects all my data source attributes. So in this case, the shortest path is this one in orange. If you see these specific cases, this edge is not highlighted because the weight, the cost that connects to these two classes is 6. So the cost of the entire path would be, for instance, 1, 7, and 8. So if we assign the correct cost, then the path is this one, because in this case, the entire cost of the path is 4. So the idea is, okay, I have to try to identify an algorithm to identify, to assign the correct costs that are able to express the correct semantics of my data source. So in this case, to address this specific task, I used graph neural networks, in particular, an approach that is called a graph autoencoder. And the idea of graph autoencoder is the idea that I described in the previous slide. So you have, in this case, an encoder, which compute the aggregation of the neighbor structure to the central node. And then you can exploit this aggregation to assign, to, let me say, score a link between two different nodes. And this link obviously was not included in our training dataset. So at the end of this process, the output is the output are the embeddings of the subject of the relations and object. And we can exploit these embeddings to assign the costs to the integration graph that includes all the plausible semantic models and semantic relations that can be used to describe my data source. So also in this case, I suggest an article on Medium that describe how to use semantic models for constructing knowledge graphs. And in this case, I also suggest a reading that is a journal paper that we have published in the last year, in 2020, that describe all the details related to the semi-architecture and all the results that we were able to achieve in the evaluation of our approach. So the second task was related to the link prediction for recommendation and the semantic search. In this case, we started from Iris. That is the tool that we used at the Polytechnic of Turin in order to publish and release our publications. So it's a search engine that indexes all the publications that are written by researchers of the Polytechnic of Turin. Actually, it uses a simple search engine that exploits keywords in order to retrieve the publications. And this is a clear example because if you type carbon nanotubes on the search engine of Iris, you retrieve all these publications, but you retrieve also different keywords that are used by the authors in order to tag their publications. So for instance, here you can see carbon nanotubes, and here you can see CNT. So in this case, we have the same concepts described using different keywords. And in this case, we achieved 27 publications for carbon that are tagged using carbon nanotubes and 7 publications that are tagged using CNT. So if I was a search engine, I expect that searching for CNT, I obtain the same results. But it is a keyword search engine. So if I type CNT, in this case, we obtain totally different results because we obtain, in this case, 9 publications with CNT and only 6 publications that are labeled using carbon nanotubes. For this reason, we used a semantic technology in order to extract the topics from the outside of the publications. So the main idea is that we try to automatize the label of our publication, not using just keywords, but using semantic concepts. And when using semantic concepts, we were able to achieve and let me say, gather under the umbrella of carbon nanotube, all the publications that are related to carbon nanotubes. Also in the cases if they use CNT in their abstract keywords or different other ways in order to identify carbon nanotube, other acronym, and etc. The main idea is try to identify semantic integration in order, try to use semantic integration in order to identifying the same concepts for different keywords. This is a dimension of the knowledge graphs that we have built using the iris data. So these are the keywords of that have been used by the authors in order to label the publications, and these are the automatically extracted topics. So this is interesting because now we have reduced the space of search because we can use directly these semantic topics to retrieve the publications. This is an example of the recommendation. In this case, you can see the page of Francesca Noardo. It is a researcher of the Polytechnic of Turin that is interested in these topics: data modeling, ontology, database, etc. Our system recommends Gianluca Parravati as an author that can be, let me say, that has never been co-authors of Francesca Noardo. So this is important. They've never been co-authors. But the tool suggests Gianluca Parravati has a good collaboration opportunity for Francesca Noardo because, let me say, he is in some way linked in a closer graph structure. And for instance, if we take an example of article that has been written by Gianluca Parravati, as you can see how in this specific article, they use the word semantics, and this article in general talk about semantics. So there are interesting collaboration opportunities between these two authors because they, let me say, cover the same topics on the one side, but they are included in similar graph structures from the graph perspective of the knowledge graph. So finally, I will show you how my reflections related to the hybrid technologies that include symbolic and vector representation to create unexplainable artificial intelligence. So we should start on the idea of the artificial intelligence. So what is artificial intelligence? Well, from my perspective, the definition of artificial intelligence is closest to knowledge graph. Well, before we see a diagram, Venn diagram, that try to describe the artificial intelligence using technologies. This Venn diagram, you can find it in the book entitled Deep Learning from Goodfellow, Benjo, and Carville. And you can see how this Venn diagram describes only technologies and approaches. Representation learning and deep learning cover, let me say, graph representation learning, while knowledge bases cover the symbolic representation of knowledge graphs. So, as I said before, my definition, my personal perspective knowledge graphs of artificial intelligence, is a way to incorporate human knowledge into machines. But how we can incorporate human knowledge into machines? But in traditional deep learning techniques that are also called inductive technologies, the idea is to learn and teach something to the machines from examples. So the machine sees a lot of examples, and that is able to generalize the behavior in order to, for instance, predict something, or label something, label, for instance, an image, etc. This specific approach, as you probably know, the learning process is actually an optimization process because I want to minimize a cost function using learning specific parameters. This learning process is based on the perception of patterns and irregularities included in the data, and it's difficult to understand. This process is difficult to understand for human beings. In general, human beings are not able to interpret the behavior of a neural network, for instance. On the other side, other AI systems can be can be learned using a deductive approach. So the main idea in this case, and it was the idea of artificial intelligence in 60s and 70s, is that, okay, I can create an intelligent system if I encode all possible rules, all possible axioms in my systems. And you can see that there is a sort of analogy with this type of approaches and the symbolic representation of knowledge graphs. Compared to the inductive approaches based on deep neural networks, for instance, in this case, the learning process is the result of symbolic manipulations. It exploits reasoning over assertion and rules, so we can learn directly and inference new edges, for instance, based on the existing rules that describe my domain. And it is completely, in general, it is completely explainable. So we are able to interpret the result of deductive approaches and go back to the origin. So we are able to understand why this is the result of the learning process. So considering both this perspective on explainable AI, we can see the explainable artificial intelligence at different levels. At the lowest level, we have opaque systems, which are completely black box. Actually, this includes all the systems that we use as a service. For instance, when you try to request on demand the service from IBM Watson or the service from Amazon Comprehend, etc. Actually, this is not directly related to the technology, but it's an argument related to the closed or open source or closed or open data. The second level of interpretability is the level in which the users can analyze, let me say, mathematically what happens under the hood of the systems. In this case, we can talk and we can describe this behavior as transparency, because in this specific case, the system is transparent and we can understand what happens under the hood. Actually, this is interpretable and transparent for all people that are able to understand, let me say, the mathematical operations that happens under the hood of a neural network. Third level is a comprehensible systems in which the system is able to answer using a post hoc explanation, for instance, a natural language explanation or an image as explanation when we try to perform a question. And knowledge graphs are particularly useful because for this specific interpretation of explainable AI, because you can perform queries on a knowledge graph. And the last level of system of explainable AIs is automatic explanations. So in this specific case, the system try to explain itself without any question from the human being. It tries to explain what happens, why the results achieved are this one and not the other one. So in literature, this behavior in general is called reasoning. For these reasons, according to these reflections, I try to identify a potential architecture in order to create an explainable AI that is comprehensible also to non-insiders of artificial intelligence. The main idea is to perform a knowledge matching process in which the components of a traditional deep learning architecture, so the inputs, the hidden layers or computational units, and the results of these deep learning architectures are matched to a semantic technology in which all the nodes and edges are interpretable for the human being. And we are able to map, to perform this matching process. On the one side, we can create the conditions for interactive explanations because knowledge graphs are directly queryable, but you are enable the conditions also for cross-disciplinary explanations because as you can see, knowledge graphs can cover different domains. So these are the suggested readings for the last part of my presentation. An article, a medium article, and a paper that is published on the Information Journal. And maybe in order to clarify and to have an intuition and an awareness on the importance of this topic, here you can see that our paper was one of the top 10 most downloaded articles in 2020. And the conclusions of my presentation, we have seen an overview on knowledge graphs from different perspectives. We can see that knowledge graphs can be represented using different structures or primitives. And we will see that exploiting the hybrid perspectives on knowledge graphs, so the semantic technologies, and let me say relational artificial intelligence, we can build intelligent in some way applications. And in regards to the future direction of hybrid systems, I believe that symbolic techniques can be used to design novel neural architectures that will be natively able to natively encode explanations. An interesting thing also will be multi-modal explanations, so a tool that is able to convey natural language text, images, or videos, and just to use different type of languages in order to provide explanations. And the idea is that if we are able to create a common explanation framework, we can also use and identify also, let me say, reliable validation strategies. Because if you want to use artificial intelligence systems in our daily life, in all the technologies related to our daily life, in particular in the case in which there are some problems related to fairness, justice, health, we need a framework in order to evaluate the results, but also the explanations of our systems. So thank you very much for your attention. I know that I give you a lot of details, a lot of stuff, but I hope that it was, let me say, quite clear. Thank you very much.
Hi, Giuseppe. Thank you a lot for your presentation. And I mean, does someone from the audience have some questions, some perplexities that you want to share? Okay, we have a question in the chat.
Okay, I have to go back in the how knowledge mapping works. We know that complex ladder representation, do we lose the... Thank you very much, Francesco, for your question. Actually, I completely agree with you. The main idea is that when you have latent representations in the that you are able to achieve during the training process, you have a lot of information that actually that is hidden for human beings, because vectors are not so understandable by human beings. But when we try to map this vector representation in knowledge graphs, we perform a sort of a sampling process. So we simplify the representation using symbol. And as you probably know, when you apply a sampling process, we lose information, but on the other side, maybe we gain on interpretability, understanding of the results and of the model. But that's the trade-off. A better interpretability means worse representation for our data.
Any more questions, guys?
Actually, in all the Medium articles that I shared with you, you can find much more details. And I show you also some NumPy implementations, for instance, for graph neural networks, for traditional graphs, or for multi-relational graphs. So this you can find also the implementations, and you can see what happens under the hood, because in many cases you have a lot of libraries and examples that obviously hide what happens at the matrix level. But in these articles, I try to show you how the matrix multiplication is performed, and etc. So questions from Alex. It's not directly related to the presentation, but okay, pros and cons of the academic world. Well, in general, the main idea of the activities that you do in academic and in universities that is research. And in general, you should have enough time and freedom also to reach bad results or bad conclusions. So the idea is that when you make research, in particular when you make a PhD program, in general in Italy you have 3 years, but in other countries you have at least 4 years. You have the time to study a lot of details on a specific topic, and you have the time also to make wrong experiments, to reach wrong solutions. So the idea is that, okay, you have there are some conditions in order to make research. And on the other side, well, the problem is that in general, in the research activities, your activities depends on your publications. So in many cases, you are not able to apply what you study in a real case, because in many cases, your main goal is to reach or overcome the state of real results on a specific topic. And maybe in some cases, it is not so funny, it's not so interesting. But on the other side, another pro aspect is that if you do a PhD in a very good environment, in a very good university, you have the chance to get in touch with a lot of other researchers that in many cases can guide you or can give you some suggestions in order to make your research. Because in many cases, in particular at the beginning of a PhD program, you have not a clear idea of what happened in the previous years. And in many cases, you risk to invent the water, okay? So the idea is to try to create also connection within the research community in order to have a better awareness of what happens in the research community. Okay. In order to respond to the answer of F. Montagna, Okay, the topic extraction in scientific domain currently is not performed directly using graph neural networks. I will share you the link of a tool that is currently under maintenance, but it's the tool that we adopted for the extraction of the topics from the abstracts of the publications. This is the tool that we have developed at the Nexa Center, and the main idea is that actually uses a simple TF-IDF algorithm that is a well-known algorithm in information retrieval. And the main idea is that we assign a vector representation to the words of our training set using the term frequency, so the co-occurrence of the words in the text. And we use also as a parameter the inverse frequency in the total corpus of our collection of documents. So the main idea, I try to provide you an example. Imagine the word Recanati. Recanati is the birthplace of Giacomo Leopardi, the poet. Maybe in a document of Giacomo Leopardi, Recanati is mentioned a lot of times. But in our entire corpus of documents that, for instance, cover all the Wikipedia documents, Recanati is not so common, probably. So considering these two specific features, Recanati is a concept that is very close to Giacomo Leopardi, and maybe it can be a result in which Giacomo Leopardi, in a document in which Giacomo Leopardi is mentioned. So that's the high-level idea of the tool, but it doesn't exploit any type of graph neural networks or any type of transformer techniques. Actually, the graph networks in the academic example has been used just for the recommendation purpose. So just to identify which is a good link, so a good collaboration opportunity between the different researchers. Actually, the maintenance of Temis first was almost concluded. So I believe that tomorrow morning you can use the tool and you can exploit it. You can, it works also for English and Italian documents. And we also provide the web API, REST API. So if you want to integrate Temis first in your applications, you can do that. There is a rich documentation on GitHub. So if you want to use it, it's free. It's not free for building tools for gaining money, because the current license does not allow this. But if you want to use it for your academic projects, it's free.
Okay, guys, any more curiosities? Any more questions? Okay, it seems like there are no further questions. And if that is so, I would like to thank again Giuseppe.
Thank you very much.
Because it was extremely available and nice for this presentation. It was very interesting. And well, I'd like to thank you again. And I hope to see you soon, maybe for some other event or some other initiative.
Sure. I will give you also the access to the slides, so you can see it again. You can use the links and
yeah, we will share them with our network.
okay.